Hi, and welcome to the Origins Podcast. I'm your host, Lawrence Krauss. Today's episode, I got to have a conversation with an old friend and colleague and collaborator, the renowned astrophysicist, Michael Turner. Michael has had a distinguished career at the University of Chicago as a endowed chair, but also as president of the American Physical Society, and for a while as associate director for physics and mathematics at the National Science Foundation. Michael is often sought out to describe and explain cosmology and astrophysics, and during my own career and in our collaborations, I've learned a lot from him. He's a lovely human being, a wonderful raconteur, and also a wonderful expositor of science. And we discussed in this podcast not only his own background, about which I learned during the podcast, many things I hadn't known before, but I wanted to discuss with him the key outstanding problems in cosmology. This podcast is, if you wish, a state of the universe report. And we discussed everything from dark matter and dark energy to Big Bang nucleosynthesis and the current tension and puzzles that are happening that you often hear about on the news, and many of which, of course, are hyped on the news. And we wanted to go in the background behind it. And we talked about our own experiences and our own collaborations. It was a wonderful discussion about the history of cosmology during the last 40 years or so, during his career and mine. And I hope you enjoy the discussion as much as I did. You can watch the podcast ad-free on our Critical Mass Substack site. And if you subscribe to that site, it will support the Origins Project Foundation, the nonprofit foundation that produces this podcast. Or you can watch it on our YouTube channel or listen to it on any podcast listening site. No matter how you watch or listen to it, I think you'll find the discussion with Michael Turner both enjoyable, entertaining, and highly informative. With no further ado, Michael Turner. Well, Michael Turner, it is so nice to be with you. It's been a while since I've been with you in person, and it's great to have you on the program. I really appreciate you being here.
It's my pleasure to be here, and it's fun to see you and talk cosmology.
Yeah, we're going to talk cosmology. I was thinking about this. I was trying to think which of your many official and officious titles I should use. But because you were president of the American Physical Society, I was thinking we should title this the State of the Universe Report. And the first thing I was going to ask you is, what's the state of the universe?
Well, the state of the universe is good.
That's exactly what I'd hoped you'd say.
The state of the universe is exciting. When I started in cosmology in 1980, roughly speaking, so that's not quite 50 years ago, I never would have dreamed that we would know as much as we do right now. So this is, it's all icing on the cake, but that's not enough. I mean, that would be great. That would make it wonderful. But as you learn more, you get to ask deeper questions. Mm-hmm. And so your standards get higher. You get greedy. And so the state of cosmology is wonderful because we can trace our understanding back to a fraction of a second. We could argue, exactly which fraction, and probably we'll get into that. But there are big puzzles that we would never have imagined. We couldn't have even asked them in 1980. Here's a big difference. The enterprise cosmology is now industrial class science. And so when you and I were young, we were part of the invasion of physicists into the realm of cosmology, which was owned by about 30 astronomers, maybe not even 30. We could argue about how many. It wasn't 100. Now, probably if you asked how many people call themselves a cosmologist or someone who studies the origin and evolution of the universe, it's got to be in the thousands. Probably not 10,000, but it must be several thousand.
Yeah, no, it's changed dramatically. I mean, we're going to get there. But in the context of getting there, this is the Origins podcast. And I don't want to talk about just the origin of the universe. I want to talk about the origins of Michael Turner. So I want to start there because, I've known you for 40 years. And I have to say, it's really true. Some of my favorite papers that I've ever written were written with you.
Oh, that's so nice of you to say.
But there's some of your background, even though I know a lot of it, that I don't know. And I wanted to go back. You grew up in LA, but I really don't know much else other than the fact that you grew up in LA. I don't know what your parents did, what got you interested in science. So I thought I would ask that to begin.
Well, I did grow up in LA, and I'm back in LA, which is kind of fun. Yeah. Well, my father was an accountant, but he was more kind of a entrepreneur, uh, but not venture capital entrepreneur. You know, he had a private practice, and he went from this and that, and he owned an ushering company, which I worked at when I grew up. My parents were divorced when I was very young, and probably people don't understand that today. It was a very big deal back then.
Yeah. Now it's so
Because
regular.
now it's a big deal if your parents are married.
Yeah, yeah.
Or have ever been married.
Yeah.
And it shaped my life in ways I don't really understand. Maybe it made me more private because it was something, kids don't like to be different. But there's some fun stories that go with it. And one is my mother sent me to a school in Santa Monica that you could drop the kids off. She had to work. She was a single mom and with two children, and she could drop the kids off at 8 a.m. and pick them up at 5. I don't think I need to describe it anything other than to give its name, Children's Paradise. So you can imagine how bad it was. And so I have told many, many people, especially my wife, about it, and they didn't really believe the stories. For example, I'd tell the story, which is probably not true, but I think it was true to my perception. I hate one of the few things I hate are beets.
Okay.
Why do I hate beets? Because they serve beets at lunch every day. Now, that cannot possibly be true, but I saved an enormous amount of psychiatry by just not eating beets. I mean, I could have gone and seen a therapist and eventually get all the transference off of beets.
Nowadays, if that happened, that's exactly what you'd be doing. And probably also feeling victimized for having had to eat them. But
so my wife kind of believed this, and it's now torn down. And I don't know how she ever found this. We were Googling. We were trying to find out exactly what it was. So do you know the novelist James Ellroy?
yes.
He's about my age, maybe 1 or 2 years older. And in one of his, I hope I got his name right. I'm pretty sure it's James Ellroy. In one of his autobiographical things, he talked about going to Children's Paradise and how awful it was.
So it's been
And
validated.
I think it's James Ellroy who got obsessed with his mother's murder. Do I have the right one?
Oh, I think vaguely that rings a bell.
So I'm not 100% sure I have the right name, but and he said that Children's Paradise had been created for divorced moms, where you could park your kids, you could pick them at 5. There were some more sordid details in there that he added. He talked about how bad it was, and everyone got passing grades.
But in spite of this, if everyone gets passing grades, in spite of this, you learned something, or you apparently learned something because you went to Caltech.
So we moved and to Westwood. We were living in, I forget where we were living. I started going to the public schools. And so my wife's theory is that I was really studious and well-behaved because when you're that young, I was in 2nd grade. I was a 1st or 2nd grader. You're trying to communicate to your parents. You don't want to go back to the other place. So I'm going to be on my best behavior here. I don't know how well that works, but Children's Paradise, I don't know that I learned anything, but then I was in the public schools at the best possible time ever. I like to say that the public schools in Los Angeles in the 50s and 60s, that's the best education money could buy. The kids I went to school with, my classmates at University High School, Bonnie Raitt, Jeff Bridges.
So they all did pretty well, but what happened to you?
Well, the school, it was a different time. The kids didn't go to private schools. If there was some problem with the parents or the kids, they went to private schools, but you certainly wouldn't go there to get a better education.
Yeah.
And so I had 3 teachers who were absolutely inspirational. One of whom died a few years ago, a math teacher, and the other 2 are still alive, and I am in regular correspondence with them. In fact, the physics teacher I see all the time. But it was the public schools. And then to bring it, since you brought up Caltech, my parents really, my dad wanted me to be an engineer.
I was going to ask, so, who had the bigger influence, the school or at home? Did your father interest you in science and maybe reading? Was there a lot of that at home at all, or did they encourage you or they wanted you to be an engineer, which is a professional?
No, I would say because I saw my father on Sundays. So it was one of these, you spend time with your father on Sundays, which is a very difficult. So you have two
Sure.
worlds, and,
Yeah.
one world when you're that young and nerdy is way too much
Yeah.
anyway. So it was really school and the support of my parents but they didn't really.
Well, I'm going to interrupt you. You said what your father did. Your mother worked too. What did she work at? Did she?
So she worked at the Rand Corporation as a
Ah,
secretary.
oh, is it?
And actually, that you will know some of the names. One of the people that she worked with over the years was Albert Wolfstetter. He and his wife Roberta were two of the nicest people I ever met, and I remember one time they liked to work from home up in the Hollywood Hills, and so my mother would go up there and work. And one time, Albert had a party for young intellectuals. Among the people I met there was Paul Wolfowitz.
Oh.
And
I
it
met him
was,
years later, by the way. But anyway.
yeah. And so it was, I'll tell you the story of how I went to Caltech was that I got involved in electronics and ham radio when I was in junior high. Then I was in love with math until I met physics. And then I still have actually I have a copy of a faded Polaroid where the physics teacher made me stand next to a blackboard that says, "Math is but a tool." The physics teacher took us to the Monday night lectures at Caltech. This was in the days there were no seat belts, there were no permission forms.
Yeah.
And there was the chemistry teacher was buying some of us chemicals to make explosives. And so it was a very different time. And I said, that's what I want to do. That's where I'm going. And so I applied to Caltech, MIT, Stanford. I was already taking classes at UCLA. My mother wanted me to go to Stanford because it would make me more well-rounded. My father wanted me to go to MIT because he had worked at Douglas Aircraft, and the engineers said MIT and engineering was a really big deal. And I knew I wanted to go to Caltech. And so my mother said, okay, I'm going to take you to Rand. There were brothers there. There were a lot of really important people at Rand. And there were Dick Latter was head of the physics department there. He explained to my mother, probably mansplained to my mother, Caltech was a very special place. And if I had been admitted to Caltech, I had to go to Caltech.
Oh.
But I wanted to go to Caltech.
I shouldn't ask, did you get in all the places you applied?
I did.
Wow. Jeez.
Well, it was a very, 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 very different time.
It was a different time. Absolutely. I was going to say that, but I'm glad you did.
And getting into Stanford was very funny because this physics teacher let us come up to his classroom at lunch and hang out. The nerds hang out. And so one day he was sick, but somehow his classroom was still open. So a bunch of us were up there, threw some water balloons down on the cool kids. And so the physics teacher comes back the next day with the serious face saying, Mike, I have to ask you something, and you have to tell me the truth. I want you to tell me who threw the water balloons. And I said, I did. And he couldn't believe it. So he sent me to the principal's office. And the principal was a Stanford graduate who I didn't really know. And he said, I can't believe that you turned yourself in. I can't believe how honest you are. Can I write a letter of recommendation for you to go to Stanford?
It's like George Washington, right? It's that story all over again.
And then there's more on the Stanford story. Stanford just released their expose of their Jewish quota. So I read through it, and it was quite interesting. Stanford was not quite as smart as Harvard, and I put smart in there. Harvard would grade the applicants on J1 through 5. So J1, definitely Jewish. J through J3, pretty much Jewish. You get the idea. Stanford was still in that time a California school.
Yeah, it was California school.
And most of the Jews came from Southern California. And most of them came from 3 high schools. One of them was Beverly Hills High, Fairfax High, which probably 100% Jewish, and Uni High. And so some smart admissions person said, instead of admitting 30 a year from each of those schools, so they did 30, they went down to about 5. And so, well, I'm not Jewish, and Turner's not a very Jewish name. So even though they had reduced the admissions from 30 to 5, I probably looked pretty safe. But it was such a different time. And, one last little quip here is that you're growing up and your world is so small. I thought the population of the United States was 80% Jewish and about 15% Mormon, because the neighborhood I lived in was right near the Mormon temple. West Los Angeles, most of my friends were Jews. I thought Yom Kippur and Rosh Hashanah were national holidays.
By the way, speaking of the Jewish thing, I don't know if you read my book on Feynman, but you probably know the story anyway. But Feynman, nearly didn't get into Princeton because he was Jewish. And the chairman of the physics department at MIT wrote the chairman of the physics department at Princeton, where he'd applied to graduate school, saying he's not too Jewish. He's not very Jewish. And that was, and because they asked, and they would, if he hadn't gotten that, Feynman wouldn't have got into Princeton. Well, you made it to Caltech, and you did physics, but did an interest in astronomy begin to blossom there, or no?
No, absolutely not. Caltech is such a serious place that you're either a physicist or an astronomer. There weren't very many. There were some.
Well, there were different worlds back then. They really were. I mean, even when I started teaching, and I was in both departments at Yale. I remember I was in physics and astronomy, and it were just worlds apart at that time. I must have asked you this, but did you take any classes from Feynman or no?
Not only did I take a couple of classes from him, again, this is the late 60s, and Caltech is trying to be a little more relevant, and so we all took physics together. At Caltech, every student had to take 2 years of physics, and we took the Physics 1 and Physics 2 together as a class, but the classes were pretty small. There were only 200 in the incoming class. Right, and my second year there, they said, okay, we're going to, I don't know if there's any students interested in a tutorial with a professor. So I, of course, was very interested, but I'm a T. So they ran out of professors. And the person actually teaching the course and doing this was a guy named Robbie Vogt. And Robbie knew me and said, I think I can find someone for you. And I see your face, and you know who he found, which was Feynman.
Yeah.
So
wow.
For one whole quarter, I would come visit Feynman once a week, and he would give me things to think about.
A dream come true for most kids.
At one of these times, Feynman looked at me the way I'm looking at you, but I got to get a little closer to look right at you. And he said, I envy your ignorance. What am I going to say? Today maybe I would have filed a student complaint or something. And I just kind of nodded my head. Yeah. And it took me about 40 years to understand it. Theoretical physicists can really understand it very well, because what he was really saying was a very big compliment, was that, when you're young, your mind is not polluted with too much knowledge. You don't have the burden of too much knowledge. And so you get an idea and it's wrong.
Yeah.
Maybe it's right.
Yeah.
But even if it's right, when you first get it, you don't get it in the right way. And so the older you are, you get an idea and you say, this is wrong. You don't even pursue it. And so what he meant was that when you're a young mind, because of its ignorance, play is more creative.
That was his characteristic. Again, I don't know if you ever, I'll have to send you my book on Feynman, which was The Labor of Love. But one of his strengths, as well as his failings, of course, was that he had to discover everything himself. In a number of cases, as he could have gone further than he did if he'd allowed himself to learn what was actually happening instead of discovering it for himself. But that was also his greatest strength at the same time.
Well, you never know that. And this, he was really saying something slightly different, which is ideas are hard. I tell the students that I work with now, look, I want to hear your ideas, because when you get old, you can tear apart, you can analyze ideas really quickly. You can get to the heart of it, and you can find all the things wrong. The other trouble with too much knowledge is, you know this, most new ideas are wrong.
Yeah.
And so if somebody comes up with you with a new idea, if somebody sends me an email with a new idea, the safe money is to say that's wrong.
Yeah, exactly.
Because 99.999% of the time, that's correct. Even if the email came from Ed Witten. I mean, well, maybe with Ed, it's only 99, but ideas, getting those ideas is hard. And so that I like to think he was saying, when you're young, you can play with an idea and let it and follow it. And most times it won't work out,
But the process is one of discovery and
well,
enjoyment.
and if a new idea is to work out, it's going to get changed. And so I used to write for Physics Today, the reference frame. I didn't write that long, but I had one ready to go on wrong papers. Every time I've told someone this, that everybody loves to hear it, which is the importance of wrong papers. And you name it. And it goes back to Pauly's, your paper isn't even
wrong. Yeah.
Because wrong can be really interesting. So, for example, Andre Limday's paper on inflation is brilliant, but there aren't any correct equations in it. But that's okay, because the importance is the idea of string theory. You name it. The number Gamoff's paper on the Big Bang, the hot Big Bang. So he invented the hot Big Bang, but everything in it was wrong. Well, he invented the R process. In fact, what's sort of amusing, he invented the R process. But this creative process, rarely do you end up with, okay, I wrote my paper, no one's ever seen this before, and it's absolutely correct. There is not anything wrong. It's usually got massive, for example, our good friend Shelley Glashow invented SU2 cross U1, but it didn't work because the weak boson, the W and the C would be massless, so he threw it away. Steve Weinberg reinvented it. It took a while for Shelley to remember that he had actually invented this theory, and Weinberg had added, made it workable by adding the Higgs sector. There's just so many examples of that in science where the key idea, when it first comes, is wrong, misguided, going in the wrong direction. There are other examples of wrong things where it was wrong, but it got somebody thinking about something else.
Speaking of wrong and misguided, let's go back to you. No, but we'll tread over this lightly because I don't know. So you graduated from Caltech, and then it took you you went to Stanford. It took you 8 years to get your PhD. So there must have been something, at least when I look at your, I
think it's only 7 years. But,
okay, fine. 7 years. You're probably only allowed 7. But anyway, it took you a while. Is it because you were wandering around trying to find what you wanted to do, or?
I went up there
to Stanford. Finally, your mother was happy you were finally at Stanford. But anyway.
Yeah. Well, Feynman told me to go to Stanford, which was another story. Was I didn't realize that Feynman only thought of himself. What Feynman was really saying is, if I were your age, I would go to Stanford, which is a good answer anyway.
Yeah. And at that time, there were a lot of, the accelerator there was producing a lot of physics that was relevant.
Well, so that's when quarks were being discovered. The more I tell you about my wanderings at Stanford, the more confusing it will become, because I was at SLAC and I wanted to do particle theory, and there were a lot of good people there. John Ellis was a postdoc, Sid Drell and BJ Bjorkane were the resident theorists, and quarks were being discovered. And then, if you start adding up the numbers, now I'm going to get the year wrong. I guess it was 74.
It started 72, actually, a little earlier.
No, it was not 72. It was either 73 or 74.
Well, it depends with the experimental revolution, or anyway, it was around then. We won't disagree.
But I got disillusioned with particle physics. I was living with medical students, and I was questioning, the Vietnam War was raging on. I was questioning, oh my God, they'd come home not drenched in blood, but I exaggerate, but they've just been saving lives. So I took I actually took 2 years off, one officially, and I was an animal caretaker at the hospital. Oh. So that gave me, I guess I only worked on the weekends. That gave me my weeks free.
Oh, wow.
And
Great
I
job.
became an auto mechanic. I got interested in relativity. And one of the best teachers was teaching a course on relativity, and that's where I got introduced to Weinberg's book. And I think I was still on leave when I took the course. And I thought, this is ridiculous. I either leave Stanford now and go do something else, or if I'm just going to live in Palo Alto sitting in on courses, I may as well get a PhD. So there was one professor at Stanford who had money for a student because he's the most underrated supervisor, Bob Wagner.
I was going to say Bob Wagner. I was betting
And
on it.
he was a fantastic supervisor. Everybody else wanted to work with people whose names I won't tell you, but they were very gentle. These other people were very gentle. You got a pre-practice problem, a practice problem, and then a thesis problem. You got to see your advisor once a week. You had a notebook. You had a fountain pen. And Bob Wagner's door was always open. If I wrote something, he would read it and tell me what he thought of it. He assigned me a really hard problem to begin with, and I came back and said, I don't think I can solve that. It was pulsar magnetospheres. So I ended up getting a PhD in gravitational waves. So I worked on gravitational waves.
Oh.
And I fell under the spell of Kip Thorne, and this was 1978. The detection of gravity waves is right around the corner.
yeah.
That was a very long corner.
So it was during your PhD that you made the transition from initially wanting to do particle physics. It's funny. I never knew it because very similar to me in a sense. That was when what introduced you to sort of astronomy was it through gravitational waves, first pulsars, working with Bob Wagner, who was in the physics department, but was interested in obviously in astronomical questions. I never took a course in astronomy. Did you ever take one?
No, not until I taught one at Chicago.
Yeah, exactly. You know, I was a professor of astronomy for many years, as well as physics, as were you. But I never took a course in astronomy, which I think is important for kids to know, because you learn more after your PhD than you do before, and that's one of the really important things. But, well, at least we should all be lifelong learners. But the process of a research career, you come out and when you're a student, you think you have to know everything in order to do anything, which is the real problem. By 1980, you'd already kind of made the transition and already was becoming known as one of the early practitioners, and I ultimately put myself in that room too, although a few years later, of what is now called particle astrophysics, with the application of what we might call fundamental physics, or to try and using the universe to teach us about fundamental physics in some sense. And for me, I don't know if it was the case for you, the cosmological questions weren't as much of interest. I just saw the universe as a testing ground. There was nothing coming out of accelerators, and if I want to learn fundamental physics, how to test it, we could use the universe, which was a particle physics experiment done at least once, and that was data analysis. Those were the questions. It was only later that kind of astronomical questions began to become of interest to me. Was it a similar thing for you, or no?
I think I liked the big picture. I liked cosmology. I tell students there's lots of interesting things to do research on, but you have to get one that really, makes your heart go pitter-patter. I'm a big question guy, and so the questions in cosmology are really big.
Yeah.
And the being able to approach it from the physics side, I didn't really like the astronomy side so much. Yeah, no, I was attracted to the cosmology right away.
Well, my PhD eventually was in cosmology, but it was sort of drag, kicking, and screaming. I started mathematical physics, and it's funny because because you knew so much more astronomy than me, I always thought of you as an astronomer in a sense.
Well, I was 5 pages ahead of you.
Yeah. Okay. But you, within a few years, I mean, you spent some time at Santa Barbara, which was an interesting time, probably with overlapping with our joint friend Frank Wilczek. You were already at University of Chicago. What brought you to University of Chicago? And then your career there was significant because you helped establish what was then, I think, probably the only center for the kind of physics that we were both kind of interested in, cosmology based on or the overlap between cosmology and particle physics at Fermilab. You've co-founded it, I guess, with Rocky Kolb. What brought you to Chicago? Was it Dave Schramm? Was it?
Well, it was really Dave Schramm. It was also luck. It was like your Star Trek story, and Obama. I wanted to stay in California, and I applied for a faculty job at Cal State Fullerton. They loved me, and there were 2 jobs, and I was their first choice, so I was going to get one. So I was offered a postdoc at Chicago from Dave Schramm and one at Harvard by Bill Press.
No.
And I told Bob Wagner, and Cliff Will was one of my other mentors at Stanford, I was going to turn down the postdocs because I was getting this faculty job. And they said, well, the way it works is, sometimes those faculty jobs don't come through, which turned out to be true. And you're allowed to, if you accept a postdoc, you're allowed to decline it and take the fact. That's just a, kind of a custom in the field. So now I had to choose between Harvard and Chicago. And the phone call with Bill Press, who is a good friend now, and he started off by saying, you were Chicago's second choice, but Harvard's first choice.
Sounds like Bill Press.
So here I am. This is the first job I've ever been offered. I had no idea what he was talking about. The next thing he said was, Dave Schramm's a better recruiter than me. And
it's probably true.
I don't remember anything else he said. And what Dave Schramm said is, come to Chicago and you'll do great things. That's all I remember. And so it was an easy decision. And I came there, and the advice from Bob Wagner was kind of like the advice from my parents. So Bob Wagner took a leave and was at Chicago at the same time I was.
Oh, okay.
So he saw me getting involved in particle physics and cosmology.
Uh-huh.
And so I guess he was on sabbatical for 9 months. And his parting words were to me were, don't do particle physics and cosmology. Stick to astrophysics and gravity waves. But I'm not very good at following advice. So I was having a ball, and it was a very, very good time. It was getting in on the ground floor. There weren't that many people. Dave was a really good mentor because he was really well connected. So you mentioned Santa Barbara. So I did 2 years as a postdoc, as a Fermi Fellow. And then Dave, I don't know how he got me on the faculty, but he did.
He could do anything.
He could do a lot. And I said, but Santa Barbara offered me this 5-year position. And he said, take it, go on leave. And then I remember the other thing that Dave said to me that, oh my God, I could not believe his confidence in the world. But Dave said to me, we can start your appointment in October, or we can backdate it to July. I suggest we backdate it to July because then you can get promoted earlier. And so I'm thinking,
many people would do the opposite.
Most people nowadays, they would do the opposite. It's like, it's like delaying your kid to going to kindergarten till they're 10. He sent me off to Santa Barbara, and I went to one of their very first workshops was on the early universe. And so I met a lot of the players, and I'm not sure that Frank was there yet.
I think he was, but maybe just then.
He was just getting there, and it was a fabulous time. There were a lot of really good people there, and so my network, I mean, I didn't realize it already at Chicago. It's a place where you can get a fairly big network, and it's a really good place. But now I'm meeting people in Santa Barbara, and a lot is going on, and so things just kind of, fell into place.
Well, okay, look, so this is good. We spent, the first bit of this on your history, but learning about science. And I went back to try and find what I could find was your first papers, because I realized I didn't know what they were. And the first one that's listed, at least in Inspire, relates to Big Bang nucleosynthesis, which of course was the area that Dave Schramm was heavily involved in, although that your paper wasn't with him. It was with a number of other people. Was that your first paper?
Actually, my first paper was with Barry Barish, written when I was a senior at Caltech, on production of an alternative to the Higgs, an idea of T.D. Lee's.
Uh-huh.
And so I think it has fewer citations. But my first paper, there were a couple of papers on gravity waves.
I figured there must have been, because the first one was 1982, and by then you'd already been a faculty member for a while. But
yeah, but Big Bang nucleosynthesis was something that was very much of interest to Dave. And so that was kind of, whether you were a student, whether you were an undergraduate, a graduate student, or a postdoc, and you worked with Dave, you wrote a paper on Big Bang nucleosynthesis.
Now what I want to do is a tour of the areas I know you've worked in, and fortunately it's a tour of modern cosmology. And as I say, I've been fortunate enough to share some of that with you. But I want to talk about the key ideas and what's changed. And we'll start with Big Bang nucleosynthesis. So Big Bang nucleosynthesis, for people who aren't aware of it, is probably the first great bit of the sort of triad that proves there was a Big Bang. But in particular, it allowed the utilization of experimental data that you could measure, in this case in nuclear physics laboratories, and apply it from first principles to the universe, and you could check to see if it was right. And it took you back to a time when the universe was hot enough, when nuclear process was relevant, around 1 second old or so. There were two things that were the first standbys of sort of fundamental physics applied to cosmology. Big Bang nucleosynthesis was one, and then you later on worked on something called Baryogenesis, which we'll talk about later. This is a perfect example, I think, of the kind of thing you talked about at the beginning of our discussion. In the early days, wow. And then the more you know, there are puzzles, and then there are big puzzles, and some of the big puzzles haven't been solved. And so Big Bang nucleosynthesis beautifully predicts the abundance of light elements from, hydrogen, helium, and deuterium, and to some extent lithium, with these vary by over 10 orders of magnitude. And so that they get the things roughly correct is even amazing in the first place. But in the details, throughout our period, there were lots of controversies where it looked like there were problems. Most of them disappeared, but one still persists, and that's lithium. Take me through a little bit of that and your perception of it. Is there still a big problem? If there is, what is it, and where do you think we'll learn about it?
One thing I wanted to mention is that Bob Waggoner my thesis advisor, did the pioneering calculations, and they were very appealing because it was physics in the early universe. It was one of the great successes, the idea that the universe was a nuclear reactor when it was seconds old, and that the remains from that nuclear reactor could be used to test the conditions back then. For example, the amount of helium that's made, first of all, tells you there was a hot Big Bang. It takes you back to a second, because there's no other way to explain the large amount of helium that we see, even in the oldest samples of the universe before stars could have made the helium. Then the deuterium is very sensitive to the amount of atoms in the universe, and that was key to the dark matter problem, because dark matter was known for a very long time. So most of the matter in the universe is dark, and we don't know much about it. It could just be dark stars. But kind of a Chicago angle on this is, well, we know how much dark matter there is, and the deuterium abundance tells us something about how much ordinary matter is. And we basically started demonstrating there was a gap between the two. And the arguments are hard because deuterium wasn't well measured, and it's a complicated story, and the total amount of dark matter you needed was not well measured. So maybe you could get them close to being equal. But the deuterium, when you look at today, we say that there is absolute, smoking gun evidence that the dark matter is not ordinary matter, is not baryons. That one of the hinges on that is deuterium, and it's a 50 sigma problem. And so it's fun because we don't need any more statistics. 50 sigma never happening. What could happen is we have the whole history wrong. The final element, and I saw it drift in. I saw lithium drift in. So as you said, it is made in a teeny tiny amount. And but some very clever astronomers, two French astronomers, the Spites, demonstrated what seemed to be really good evidence that they had found the primordial abundance, that is, before stars started making lithium. Oh my God, boy, talk about fool's gold. Not that they were fools, but talk about, it was an extraordinarily good case. And it people didn't jump on it immediately. They said, okay, well, let's do this test. It passed all the tests. Now it doesn't anymore. And now that we know a lot about nucleosynthesis and a lot about how many atoms there are, it's a factor of 2 problem, which in the era of precision cosmology is a big deal. And some problems are ripe to solve. I mean, probably everyone has written a paper on here's what you change about Big Bang nucleosynthesis to get the lithium right. And all of the changes people want to do are nutty. None of them are really compelling, but you could do it. And so maybe it's teaching us something very, very subtle, or maybe not.
Yeah, I mean, I have to say, interesting. I came in from a little bit of the direction when I was at Yale. I was working with another French physicist, Pierre Demarque, and I suspect, like you do, that the problem, this is now a factor 2 problem, which in cosmology 40 years ago would have been great to get anything with many things within a factor 2. But he did solar physics, and I suspect the final answer will be some complicated aspect of the way stars process lithium. We got involved to try and see if we could resolve that problem by thinking about, how stars produce lithium and what constraints you could put on Big Bang. What is amazing is you can get the order of magnitude of lithium right, 10 orders of magnitude less than hydrogen. And so some people would say the fact that you're off by a factor 2 is not a big deal. But in this era of precision cosmology now, a factor 2 is a big enough deal that some people will at least write papers saying something fundamental has to change. My suspicion is always, and again, this is a bias. Whenever there's a disagreement between theory and observation, my immediate response is it's probably dirty astrophysics. That's complicated, but who knows what the answer is. But I think you probably agree with me. It's likely an astrophysical solution and not a cosmological one.
I think even the astrophysicists say that. But it's a lesson about science. Science is a lot about taste and timing. So I think the lithium is not ripe right now. Something will change. The stellar models, probably nothing that I could do will change. But right now, that doesn't seem to be ripe. It just, it could be the thing that, maybe that's the thread that I don't think it's the thread that will unravel everything we know about the universe. That seems very unlikely. I mean, you can't pick and choose your facts in science. I mean, have to be very careful there. I mean, sometimes facts aren't really facts, but this one, I think, in most people have it on the back shelf. And, I go to seminars and, maybe every 10th or 20th seminar, somebody says something that might be relevant, and oops, it isn't relevant. But I imagine one day something will pop up and that will get solved. Or maybe it will reveal a big secret. I mean, it could reveal a big secret because, as you pointed out, once the basic picture of nucleosynthesis is right, you realize, oh my goodness, the amount of helium made depends sensitively on conditions in the universe. And whether or not there are additional particle species in nature that we have yet to discover. And that's what Dave Schramm was involved in doing and pointing out. And it could teach you. I mean, it was the first concrete example that particle physicists would believe. They didn't believe all the numbers.
Yeah.
But this was nuclear physics, and they could say, okay, I think there's probably something wrong with one of your nuclear cross-sections. But at least it was nuclear cross-sections and not measuring photographic plates where they didn't have a shot at figuring it out. So nucleosynthesis, it's kind of probably, if you were really, really hard-nosed, it's our last known outpost moving backwards towards the Big Bang, where if you asked a bunch of and I know we don't use the word believe in science, but do you believe Big Bang nucleosynthesis really happened? And part of the reason we can say yes is, I like to say this, you can close the circle. You put in the hot Big Bang model, you add nuclear physics, not some nuclear physics you made up. The nuclear physics you measured in the laboratory, it predicts something, and it's the abundances of helium, deuterium, hydrogen, lithium. It has another prediction. I don't know if you discovered that paper. It's one of the most fun papers I ever wrote. It predicts a very subtle heating of neutrinos that can be measured. It will be very hard to be measured. But it's a subtle effect that actually you don't need Big Bang nucleosynthesis for it, but it's a subtle effect from that era. So we're down to measuring the subtle things, and the subtle things better be right. For example, Feynman's theory, QED, quantum electrodynamics, makes a prediction about the magnetic moment of the muon that's been measured. I forget how many decimal places, 10 or 11 or 12.
14, 13 or 14, something.
So if the theory, those are the kinds of theories we have. It's not just, I have a theory, all people have two legs or...
Yes. I mean, particle physics has had that level of precision for a long time. And in your and my lifetime, what's amazing is that we went from, a factor of 2 uncertainty in the Hubble constant to an era where things at the percent level are better, sometimes much better than percent level, are measured, and if there's a difference, are of concern. It's a huge evolution in a single lifetime. And I agree with you. I never thought in my lifetime we would be at that point. Now, the next topic, which is one of your next papers, but an area which I think in some ways retrospectively was the first area that got particle physicists interested in cosmology. And I think it was really first most lucidly argued by our late friend and the remarkable physicist Steven Weinberg, which is there's one fundamental number in the universe, that one, at least for particle physics, one fundamental number. The fact that the number of, for every proton in the universe, there are more or less 1 billion or 10 billion photons. That number is a fundamental characteristic of the universe. If it was a very different number, the universe would be very, very different. But it was a number without any fundamental explanation, staring physicists who were interested in that, particle physicists at least, in the face, and sort of enticing them to say, do you have enough chutzpah to suggest that you might actually explain that fundamental number? And I know Weinberg was interested early on, and around the time when you were writing and around the time when I got my PhD, for the very first time, it looked like physicists might have a shot of actually explaining that number from fundamental principles. So I'll get that introduction and I'll turn it over to you now.
You're absolutely right that that's a fundamental number. And that I think you're also right that that was really the turning point to get physicists interested, because it was at the nexus. In order to explain this number, you needed grand unified theories. These theories that unified the quarks and the leptons, at the same time unified the forces. And physicists, particularly Steve Weinberg, and Shelley and also Howard Georgi, recognized that the coupling, the strengths of the forces came together at a very large scale, and that these unified theories would make this amazing prediction that the proton is unstable, which is just crazy. That same prediction that the proton is unstable is exactly the ingredient that was needed to create the one particle for every 5 billion photons, every 2 billion photons. And so without going into all the details, there was a deep, deep connection. And I went to a meeting that David Klein organized in Wisconsin. I went up to with a graduate student. We drove up in December and it's snowing. And I'm going, are we really going to go up there and, get caught in that? We're going to drive in the snow and get caught in it. And it was a fantastic meeting. David Klein, who is no longer with us, but was just this wonderful, amazing person, particularly to young people. If David Klein gave a meeting, everyone spoke, particularly young people. I think this was December 1979. I was invited to give a talk on what's now known as baryogenesis, the origin of this number. But I got to watch at this meeting where people's eyes were bugging out because all this unification had to be true, and it could be tested by measuring, looking for proton decay. But there's much, much more. You could actually do an experiment for a few $1 million. David Klein put together an experiment. Other people put together an experiment. And, this was also a lesson. This just had to be right.
We were sure it had to be right. I remember I was in the Nexus. I was at MIT and then Harvard at that time. And it was like, I remember Shelley, and it was like, we're waiting for the next, it was the grand synthesis in the air. In fact, I went to a similar meeting that was the first meeting on grand unification. It's called the first workshop on grand. It was up in New Hampshire. And it was like, this is the celebration. We are at the point of a grand synthesis where we'll understand everything. The hubris was amazing. But there was a sense, almost a religious belief, faith, in the sense that it all seemed like it was going to come together. The new experiments would come online any day, and it would all be settled. And of course, it wasn't. But it was an amazing time.
And it's an important lesson of science, which is ugly experimental facts kill beautiful theories. And so this beautiful, very simple idea of unification just wasn't right. But it did not stop the merger, the coming together of
it caused
physics and cosmology. But it is interesting that this thing that brought everyone together, that everyone is excited about, is also on the back shelf, because it has to be true that the 2 billion photons per atom came about this way. Of course, it doesn't have to be true.
But it has to be true that some new physics, I mean, it has to be explainable.
It's been a wonderful story because the original story was very simple. It was related to proton decay in a simple way. The more complicated story that everyone thinks is more compelling today, and the story is even greater. I mean, it's like, Star Trek Volume 2, is that, well, the story's a little more complicated. The whole business starts with neutrinos. You start by making extra neutrinos, and then a part of Steve and Shelley's standard model turns these extra neutrinos into protons and neutrons. So the story is even more wonderful, and the story only works if neutrinos don't have very big masses, and they don't have very big masses. They have tiny masses.
And again, you can test part of this story. That's one of your Alma Fermi lab is, it's about the only major particle physics experiment being done in the United States, is partly to test that picture.
And it won't really completely test it, sadly. But so Jim Cronin, another ingredient to this. I mean, the story is so much more interesting because another ingredient is the slight preference of the laws of physics for matter over antimatter. That's an oversimplification. My colleague at Chicago, Jim Cronin, discovered that. And that's how we got to know one another, because he wanted to know about baryogenesis. And he, when he discovered this, he mused in his Nobel lecture whether or not this could be related to the fact that the universe is only matter. Towards the end of Jim's life, when he heard me giving talks about cosmology and the great unsolved problems, I left out baryogenesis because I left out lithium. I mean, it's on the back shelf. You only have so much time in a colloquium. You can't. And boy, did Jim spoke his mind, and I now mention it, although I say I'm not going to have time to talk about it. And so it's interesting that, again, that got everyone interested.
And right after, grand unification, the thinking about grand unification and some of the problems, actually of having a workable grand unification involves, the forces of nature look different now. And if they were looking the same back then, something had to happen. Physicists call it a phase transition. In thinking about the dynamics, a young postdoc who couldn't get a job realized something interesting, and it came out of the blue and I know for a fact many people kicked themselves afterwards, saying, why didn't I think of that? But we're talking, of course, about inflation and Alan Guth. And around that time, 80, 81, it came out like a bolt of lightning about, it basically said, not just might you solve this one problem, but you might explain why the universe looks the way it does, which most people didn't realize was a problem. I think most particle physicists didn't. You, of course, got involved in that, as we all did, and thinking about some of the ways to test inflation, and have written some, I'd say, seminal papers about that. So take me back to that time, if you can remember it.
I'm not sure that I painted myself with glory early on, but Alan wrote this amazing paper. He writes really clear papers, and I tell students and others what's really amazing about this paper is he said, I have this amazing idea and I can show it doesn't work. The amazing idea is it would explain a bunch of the features of the universe that are most prominent, its smoothness and the fact that it's so old and that it's uncurved. But he said, I can prove in gory detail that it doesn't work. But it was a call to action. And he deserves an enormous amount of credit because he said, looky here, this is really important. I'm not smart enough to get it. I mean, he didn't say it that way. The solution came from Andre Linde and Paul Steinhardt. And so by now I had met Frank Wilczek, and it was December, and Frank is just one of the more amazing people I've ever met. He's one of the people who can do really creative physics. I don't know. I don't think he can do it 24 hours a day, but most people can only do it 2 or 3, and he could easily do 10 or 12. And so it's December, not much is going on in Santa Barbara, and this preprint has arrived, and Frank says, we ought to take a look at this, and we start working through it, and there were a bunch of mistakes in it, but we realized this solved Alan's problem. And so I believe, I can't prove it, so we realized there was a friction term in this slow roll inflation. Now, we're getting a little technical. On some HP calculator, I wrote a computer program to put in the friction term and see if this all worked. And it did. I was traveling a lot in those days, and I was invited to give a talk at Penn. Maybe they were even thinking of hiring me. And I met this guy, and, physicists get together, and people say, what's happening? And I said, well, Frank and I just saw this amazing paper, and we're really taken by it, and we're trying to fix it up a little bit here. There's some problems with it. Paul Steinhardt is there, and he and his student Andy Albrecht had come at the same thing, but in a very different way.
Yeah.
And so we ended up collaborating with them. We showed some details of how this would cure the problem and reheat the universe. But the key idea was Linde and Steinhardt and Albrecht had come up with this. It's called slow roll now.
First, it was called new inflation.
It was called new inflation, and then chaotic inflation, and it all the labeling, but it hasn't really changed in, let's see, that would be 1981 or something. Yeah, so in 60 or no,
42,
40 some years. It's
in the cosmological sense, you're close.
That then led to a workshop in Cambridge, the most exciting meeting I've ever been to. So Stephen Hawking, the luckiest and the most unluckiest person in the world, had some money from the Nuffield Foundation, and he and Gary Gibbons were doing meetings on quantum gravity, which both of us roll our eyes at a little bit. It was not our cup of tea, would be the thing to say. And Stephen got interested in the early universe, and they decided he just had a feeling that this was going to be big. And so he invited a bunch of people. He got some Russians out, and the way he got Linde out was he contacted the academicians and said, would you like to come to Cambridge? And by the way, could you bring Linde, Dolgoff, and Starobinsky, who are the ones that they really wanted? And so this meeting became more and more exciting. And this is the meeting where we figured out how the universe got its lumps.
The key point, which is really more important than the details, is that inflation is and I think you'll agree with me, it's the only first principles theory that can explain why the universe looks the way it does in a general sense. And in fact, you and I later on utilized that when a lot of astronomers might not have believed it. One of the predictions generically, sort of inflation, is that the universe has to be more or less flat. And we certainly utilized that in later on, which we'll talk about. So that was wonderful. But the amazing thing was it could actually make a prediction of something that hadn't been seen. The universe was observed to be roughly flat and the cosmic background existed and there weren't monopoles and blah, blah, blah. And it was old, but there are lumps. And those lumps until that point were an act of God as far as any physics was concerned. No one, I think, before inflation ever felt that fundamental physics that was known at the time, without some theory of quantum gravity or some theory of the origin of the universe, could actually make prediction, explain why you and I are here. The lumps in your office are there, and the lumps in the galaxies. At that meeting, a bunch of people, including you, and a bunch of people did fundamental calculations, and all came more or less to agreement that, hey, it could probably explain the general features that had to been observed for why the universe was as lumpy as it was. And then, of course, years later, made a prediction about what the kind of lumps that should be observed in what's called the cosmic microwave background should be. And probably the most important, I think, for many people, and I want to see if you agree, that's kind of, if you had to think of a reason to believe that inflation happened, and again, we don't use the word believe, but to trust, to say it's highly likely, even though we don't have a theory of inflation, you and I would say it's so, as Einstein would have said, it's so beautiful that if nature has to have adopted it at some level. Can I have your comments on that?
If we had the curve in front of us, I think even if people don't understand what the curve is, you see about 2,000 data points, and there's a curve that goes through all of them. And the meeting, just to add a little color to the meeting, I showed up at the meeting. Paul and I had been calculating how the universe got its lumps. Mm-hmm. And we show up, and when you go to a scientific meeting and you're young, you come with a paper. And so Stephen was there to greet us. And Stephen, I said, we have a paper for you. Mm-hmm. And Stephen says, I have a paper for you. And so he had been thinking about the same thing, and our answers were different. Also at the meeting, so that's two groups. Also at the meeting was Starobinsky, and he had a calculation, and it was different as well. And the fourth person working on it was Alan Guth, who is so careful that he didn't have an answer yet. By the end of the meeting, and word just spread like wildfire, because as you say, if this is true, this is really important. And it's a real prediction. And so word spread like wildfire. And people would come up to me and say, I think you and Paul are right. But the same people probably went up to Stephen. And clearly not everyone could be right because, and it turned out that Alan didn't have an answer and the other three answers were wrong. And by the end of the meeting, we had all agreed on the answer using different techniques.
Yours was a complicated one, but much more complicated and using a very strict formalism that's very useful and mathematically well defined. Alan's, in the version I saw, of course, the first version was much more heuristic, and therefore, if you wanted to explain it, I used to explain it using Alan's heuristic picture, and eventually agreed with yours, but much more heuristically.
It was really fun, and we used a formalism developed by Physics is a Small World. Jim Bardeen, the son of John Bardeen, the only two-time Nobel Prize winner in physics, and he told us he was also a student of Feynman's, and he was really smart. And he told us, guys, I'm going to figure out what everyone else did wrong because you used my formalism. You must have gotten the right answer. And oh my God, if only we had laptops then, because we did everything right. Except that we had to integrate a differential equation, which now would be trivial on a laptop. Yeah. But we didn't have computers. We used approximate techniques. And unless you know the trick, integrating this equation is not so easy. And so that was our downfall. But it was a very exciting meeting. And by the end of the meeting, we had disproven, I mean, it again illustrates how science goes. So this so-called new inflation, you called it new inflation, we had shown that the lumps would be way too big.
Yeah.
In its ashes, the phoenix rose because it was now clear what you needed to do to get the right answer, to get an answer that, and so in fact, there were already people who had heard what the formula is. So here's the formula for the lumpiness. Okay, can you make a theory? Here's the formula.
Then there were thousands of theories.
Yeah, so it was very, very exciting. And so that meeting was the most exciting meeting I went to. Stephen was an amazing host. I proposed marriage to his daughter, Lucy.
Oh, wow. And she had the wisdom to turn you down, I guess.
Well, what was so funny is he hosted various social events. I mean, the whole thing was just amazing. He hosted social events, and one was a croquet party. And so I was paired up with Lucy. You know this. Stephen had an amazing sense of humor.
Yeah, absolutely.
So his daughter, I forget how old Lucy was. She was maybe only 13 then. So I was not serious, but he smiled, and you have to wait for his answer. And he says his answer is always short and pithy, unbelievably funny. There is a very long queue. It just was an amazing meeting. Nobody had ever met Andre Linde before.
Oh,
and
okay.
Martin Rees hosted a party, and Linde is a presence.
Is a presence, that's right.
And he said that he had magical skills and he could turn a white man into a black man. And oh my God, but we had to turn down the lights, and Dimitri Nanopoulos and Stephen's secretary, whose name I can't remember, were going to be his two guinea pigs.
Oh my God.
And it
I'm not sure I want to hear this story.
Candles and plates. And so what was happening was you had a plate and a candle, and you were putting the plate over the candle, blackening the bottom, and then you were touching the plate, you were rubbing your face, and there's a lot of stuff going on. And so Dimitri fell for it all, and Stephen's secretary didn't, because she didn't touch her face because she didn't want to upset her makeup. There's an amazing picture of the meeting that Andre Linde's not in, because the Russians, they couldn't get to the West very often, so they were out buying stuff.
The physics would have more or less come out one way or another, because physics, the physics is there. You gave a wonderful segue that allows me to go to the present, which is, there's a formula. We know what we need in order to get the universe to look the way it does. And there's really you may not agree with me, but there's no pretty theory that does it. You can do it. It always seems a little contrived, and it's always beauty is in the eye of the beholder. So everyone who writes down a model thinks it's beautiful, but except the other people who haven't written the model don't. And we are at this stage now, 40 years later, where I think it's fair to say that we all pretty well think that it's not everyone, including Paul Starner, has changed his mind, but the by and large, the community says, it's just so beautiful, it has to be true, but we don't know if it is, or we don't have a beautiful theory yet. We have a beautiful idea. We're at this point where, if we're lucky, the universe may give us a direct observation that harkens to only inflation, and only inflation could have produced it. Or we may be unlucky. But we're at this uncertain point where we have this idea which seems so right, but no fundamental model explain that to explain it, and we may or may not have fundamental data. So I've sort of framed that problem. Do you think I framed it right? Where do you think it's going to happen? Or do you think, of course, it's hard to predict the future, but do you see that as the problem?
Yeah, I do. It's a very attractive idea. I think it's too simple to be right. I think it's got a lot of the truth. I'm pretty sure it doesn't have all the truth. But how to get to the next level is very, very hard. And as you point out, we've got one really big handle, but boy, somebody just told you that there's a pot of gold behind that wall over there, and that wall's a really big wall, and somewhere on the wall is a button you press, and the wall opens up, and the pot and gold is there, because these gravity waves will show up in the microwave background, with a very distinctive signature, but only if inflation happened early enough.
At exactly the right time. Yeah.
And it has to happen really, really early. So early that I'm embarrassed to give the number, 10 to the minus 37 seconds. If it happened later, it could also explain the universe, but we'll never see those gravity waves.
Exactly. We'll never see it.
And there's no reason to believe. So it's kind of a shot in the dark, and you've got to go after it because it's like you're a detective. It's the only clue you have right now. It may not be that it's like the drunk who's looking for his keys under the lamppost and somebody says, "Did you lose them there?" No,
Yeah.
but this is the only place I could see them.
Absolutely. It's the only lamppost we have.
It could be an idea in theory. It could be, but it is so early on. So there was kind of a false misstep.
They were just unlucky. I mean,
They were
had all the
unlucky.
characteristics of looking right, and it was just nature fooled them.
It was a beautiful experiment, and they continue to be the most expensive. Sorry, they're not the most expensive. They're the most sensitive. I remember, I think I even wrote an editorial in Science or somewhere. So our oldest relic from the Big Bang that we know for sure is the helium you and I were talking about. And, you can quibble about, did that come from 1 second or 10 to the minus 2 seconds or 100 seconds, but it's about a second. This one, if it's found, comes not from 1 second, not from a microsecond, not from a nanosecond, but a 10 to the minus 37 second.
It's such a leap. And it would be amazing if it were a leap that's big, if it really turned out to be true. One should not have any expectation that kind of leap will work, because unfortunately, this beautiful, unbelievable discovery was wrong. And that happens. And that's the great thing about science, is that it was beautiful and we all wanted it to be right. But nature determines whether it is or not. And we have to, and the minute we know it's wrong, we throw it out like yesterday's newspaper. And it's really, that's a great thing about science, is we're willing to say we're wrong.
You don't even have to say you're wrong. I remember we were talking about magnetic monopoles, and they've been discovered many times. Only one person made a retraction. Nobody has to say they're wrong. If you can't reproduce it,
then it's exactly.
It's so science is self-correcting. So even if the person, made the putative discovery will not give in and insists till the end that they're right, if you can't reproduce it, it's not a fact.
Yeah, exactly. Well, look, let's leave inflation, but I would say the interesting thing is that my initial feeling was inflation almost exactly the same as yours. Inflation captures something right, but it's just too simple. There must be something that inflation mimics. I say that, however, I used to say the exact same thing about the Higgs mechanism. I used to say the Higgs will not be discovered at the Large Hadron Collider. It's just too simple. It's right, but it's, you don't expect new scalar particle. It must be something that it mimics, something more fundamental. Nature's not going to be that simple. So having been wrong then, I'm more chaste now.
The Higgs story is not done, and I think this story is not done. And we know general relativity is not the ultimate theory of gravity.
Yeah.
But it got a lot more than Newton's theory, and Newton's theory was a major milestone. And so I like the way you put it. Inflation has captured something. It's a little too simple. It can't be right in all the details. For example, if you take it at face value in the most simple-minded way, it predicts the multiverse.
Yeah.
And then thank goodness you don't have Paul Steinhardt in the same room as me, because he would then be saying, so therefore inflation makes no predictions, whatever, and it's not really a theory. And we would get into this argument. I don't think it's the ultimate theory, and you can't take everything it says at face value because it's too simple. And now I'm starting to sound like the fortune teller. You have to listen carefully to what I say, and I only meant the things that came out true. But but you have to look for the robust features.
Yeah.
So the Higgs mechanism has a lot of the truth in it. There is a particle. It has the properties that the simplest model would predict, but that does not mean that It could be as simple as a fundamental scalar.
Or it could be something else. You're right. That's an open question. But the fact that it was even there in even its simplest, appeared to look in its simplest form, shocked the heck. But in any case, that's the great thing. We don't know. And we know enough to know something smells right. Now let's move on. So that's where we're at in 2024, 40 years later. I want to move on to three other areas. Dark matter, which you were alluding to earlier, another area that you and I have both worked in, but was the next area. When I look at the sequence of papers of yours, it was nice to be able to go because it hits all the topics I wanted to talk about, which are the key open, outstanding questions. It was well known that there was that most of the mass in the universe was dark early on. I think most astronomers felt there's lots of places to hide normal stuff, snowballs, cosmologists, planets, lots of places where, okay, so there's a lot more out there than meets the eye. No big deal. But then Big Bang nucleosynthesis was kind of the first place. And since then, there have been a lot of other arguments that show, hey, it just can't be made of the same stuff as you and me. Many people think it's kind of like, oh, you're just inventing something to solve a problem. But what I'm going to state my perspective, and I'll see if yours is the same. I'd be surprised if it isn't, which is every model of particle physics that goes beyond the standard model more or less predicts some kind of new elementary particle, which can be abundant in the universe. And moreover, the argument I like to give is that photons are the most visible thing in the universe. But until 1965 or so, we didn't even know the cosmic microwave background was there. And all you have to be is a little less visible than photons, and you could be created in the universe and be invisible. So it's not to expect it to be some new type of elementary particle is not creating, as I think you would have said, what would you call it? You're only allowed two tooth fairies. It's not a tooth fairy. I think you and Rocky probably said that at some early point. It's the most natural thing you could possibly expect. And then the question is, can you detect it? So is my perspective in agreement with yours, or is there some nuance you can add to that?
They're kind of two big transition points for dark matter. You can trace the seeds of dark matter back to the 1920s. Most people track it back to Fritz Zwicky and his famous paper that wasn't really about dark matter. It was about tired light. He didn't believe in the cosmological redshift. Around 1980, and not to make this a PhD thesis, the astronomers started taking the dark matter problem seriously.
Yeah.
Vera Rubin played a very big role. The radio astronomers would say Vera Rubin showing that the rotation curves of galaxies were flat, that stars very far from the center of the galaxy were still moving around at very great speeds. And if all the matter were in the center of the galaxy where the light is, it wouldn't work. But the radio astronomers kind of had gotten there first. But, and this happens in science a lot, the rotation curves of galaxies were expected to be, I think they even use the word planetary. So the planets in the solar system, Pluto, I know it's not a planet.
It is for you and me.
Pluto doesn't move very fast. The inner planets move a lot faster. And the radio astronomers, using radio techniques that were very difficult, they were not easy, and an optical astronomer would have a hard time understanding or believing them because you can't see it with your eye. And so they wrote papers saying that the rotation curves were not planetary. Or maybe they used the word Keplerian. I forget which one it was.
Yeah.
They did not use the word dark matter. And when you see, I hate to use paradigm shift here, but when you see a shift, the shift came really with Vera Rubin, and also Sandy Faber deserves a lot of credit. A review article that she wrote with Jay Gallagher started saying, not only are they didn't use the word planetary, but there's dark matter there, the kind of dark matter that Fritz Zwicky and others have been talking about. So they went back and tied it all together. And so there was an IAU symposium at Princeton. If IAU does it, that's the International Astronomical Union, then it's official. That was the first meeting they had on dark matter. And actually, I have a paper there. I think it is my longest paper. I think they gave me 50 or 60 pages.
Oh,
Uh,
geez.
that's when they were being introduced to the idea of particles. The case was not compelling. And the case later became compelling a couple of years later. So that was 1980. And a couple of years later, in 1983, massive neutrinos. It's what you said, that particle physicists working on their own, trying to solve their own problems, found out they had something left over that if you put it in the Big Bang would be here today and explain the dark matter. That's way too simplified, but that's what you were saying, and that's
Yeah.
the idea. And it shouldn't be that surprising. And it's a really good lesson that I like to use when teaching classes. Electromagnetism is really important. It is our life.
Mm-hmm.
It is literally our life. We only know things that are made of charged particles and interact with photons. And there could be all kinds of other things that we're completely insensitive to because we're built of charged particles, and the way we communicate, the way we're held together. And so it's not so surprising. And then Big Bang nucleosynthesis comes back, and when the deuterium was really accurately measured, there's a real gap between the amount of dark matter. I don't care who you believe on how much dark matter there is, but the baryon number is very low. The amount of ordinary matter is very low. Now, as you say, the evidence is in the microwave background, where it's a 50 sigma difference.
Yeah.
So you don't need any more sigmas.
And the simplest, as Frank would call it, radical conservatism. The most radically conservative solution is not to assume gravity is at fault, but just that it is some new particle because they're natural to have them. You and I have both worked on two types of where there's sort of the two major paradigms of dark matter, WIMPs, and now you're attributed to, you give good names to things like dark energy, as we'll talk about later. I forget who came up with the name WIMPs. And sounds like it would be you. I know, it sounds just like a Mike Turner. So very heavy versions of neutrinos, or these weird particles, these incredibly interesting particles called axions, which are very different as any particle could be. Both of these, I call them kosher, because they're developed by particle physicists to solve particle physics problems. And after the fact, we discover that they solve a cosmological problem. Anyone can invent a new dark matter particle if all you want to do is, that's easy. But something that has a real reason to be there in particle physics. And WIMPs, especially in the case of supersymmetry, were kind of naturally predicted to be at a natural scale and naturally evolve there. Axions, not such a natural scale, but they are the most beautiful solution of a fundamental problem in particle physics, which we won't go into. And if they're at the right scale, they would beautifully form dark matter. And the great thing about both of them is that they're experimentally accessible. I would ask you, if you were like me, when the Large Hadron Collider was built, my feeling was the Higgs is really hard to find. I wouldn't be surprised if they didn't find it. Doesn't mean it's not there. It just might mean that they can't extract it from the backgrounds on. But the one thing they're sure going to see are WIMPs, because supersymmetry seems so compelling. So I kind of thought the first result that would come out of Large Hadron Collider would be WIMPs. But I was surprised and that, hey, they weren't there, at least at the level. They weren't seen immediately. And a lot of people, although I'm not one of them, a lot of people have said, oh, it's the death of supersymmetry and the death of WIMPs because they haven't been seen. So give me your perspective of both, actually, and where you think we're at, and are you discouraged or surprised, etc.?
I'm not so sure I was smart enough to say that the Higgs would be harder to find than the neutralino or the WIMP, but my colleague at Chicago, Rocky Cobb and I, were calling the 2010 to 2020 the decade of the WIMPs, because it was not only the LHC, it was other experiments that had become sensitive enough. And so we were looking for a triple signature. We were very bullish that this was going to close it out. I was there at the birth of the axion, so I was a graduate student at Stanford, and the story is complicated because it was invented by Pache and Quinn, but they didn't realize there was a particle, and Weinberg and Wilczek.
Exactly. The mechanism that solves this fundamental problem is theirs, and Stephen and Frank independently realized that a particle must be involved.
Those are the two most compelling. And I also agree with Frank and I often tell students this, that the most conservative solution is that it's a new particle. If you look at the new particles, the two most compelling are the axion and the neutralino. But as we all know, the most conservative answer is not always the correct answer. And we certainly know that beautiful theories are killed by ugly experimental effects. And in cosmology, nobody ever talks about the steady state theory anymore. I'm happy to call it the most beautiful theory because we're not stuck with it. I'm not sure it was the most beautiful theory, but it is a very beautiful theory that the universe is always the same. And it's very reassuring, and it's constantly being replenished by matter being created. But it was such a powerful and beautiful theory that it was easy to rule out. And so you made the point, in science, an important part of a theory is that it's falsifiable. So we are stuck right now, and I'll go one step further than you did. So the young people have given up on well, they've given up on WIMPs. And so they're looking for new ideas. To someone who's been around for a long time, the new ideas do not seem as compelling. They seem, and I think using your definition, they are really ad hoc.
Yeah.
They've gone looking for dark matter. They didn't find it accidentally. And so I think that's the definition of contrived. But most contrived doesn't mean wrong, because it does. In fact, we were reading in this class I'm teaching, early on in science, or sometimes scientists are embarrassed to say where they got their ideas, particularly in the early days of science, that it came in a religious stream. It doesn't really matter if it came in a religious stream or in an LSD trip. We're going to go test it.
And if it's right, it doesn't matter where it came from.
If it's right, it doesn't matter where it came from. Ramanujan imagined, could see numbers and theorems in his brain, and some of them were and they were religious when he was praying or whatever he was doing, and some of them were right. And it doesn't matter where you got the idea.
And it doesn't matter who got the idea, whether they were a nice guy or a creep or anything else. It either works or it doesn't.
At the end of the day, that's right. And so coming back to this struggle, because the real struggle, where these young people are headed, where the new generation is headed, is we had it in our heads, and it goes back to the first gut, SU5, is that we're really close to the final theory, and there's just one new piece. And so we kind of had it in our heads that there's one new piece, there's one new stable particle, that's dark matter, and we're done. What some of the younger people are saying is, no, the dark matter particle is the tip of the iceberg, and there's a whole dark world down there that barely only communicates with us via gravity. Well, it can be more subtle than that, but we only know about it because of gravity. Whereas we were saying, no, the tip of the iceberg is the stars, and the dark matter is what's below, and it's one particle. And so those are two very different pictures, both that use an iceberg. Is dark matter just the completion, or is it the portal to a whole new world? And both would be exciting. I can see the portal to the whole new world would be a little more exciting if you were younger, because there's full employment.
I sometimes say, and let me just ask you, when people ask me, my last book is about the unsolved mysteries of the universe, and at least the known unknowns, as I call it. The unknown unknowns are much more interesting, but the book is much shorter. Of all the ones in physics, the one I think, if I were to say what I, at least in my gut, think it's not unlikely would be solved, at least in my lifetime and maybe in the next decade, I keep, of all the problems, I think dark matter is still the one where if I were going to bet, we might know the answer in a decade. Would you agree or no? I mean, of course, I've been saying that for 40 years. Do you have that kind of optimism or no?
I think it's a solvable puzzle, because we do have these very sensitive experiments, and life is never as simple as you thought. And sometimes finding the new particle is easier than you thought. Not very often, but it has happened. Sometimes it's harder. Yeah, I think if I had to bet on which puzzle we solve first, because we were talking about inflation and those B modes, when you really look at the equations, and I don't want to really look at them here for two reasons. Not that it's too technical, but because it's too discouraging, is the small window you have on the world of all possible models of inflation is so small that it could be inflation is the right theory and you'll never see it. Whereas dark matter, we have not exhausted, and in fact, to give credit to the next generation, not only are they inventing new particles, but they're inventing new ways to find them. So they're making it testable. That's the good news. The part I don't ever want to tell them is that when you look at, your ideas and other people's ideas about detecting neutralinos, you and Frank wrote a paper and, this is really easy. And,
years.
Just using present technology, it took 20 or 30 years to reach. Probably they haven't reached the sensitivities that you predicted.
Yeah,
I don't
absolutely.
know. Experiment is really hard, but this is a really big problem, and it seems within reach. It does not seem unreasonable. We were at a high point of enthusiasm, of optimism in 2010, because every decade you have to think about what are we going to do in this decade, and the LHC had just turned on, and Rocky and I, and we were writing a proposal for NSF, and we called it the Decade of the WIMP. And it seemed like, I don't think we ever thought it was 100% chance, but it seemed like, if you're going to make a prediction, this would be the decade to predict that the WIMP gets detected, and it would be a pretty safe bet.
I want to move to the last of the areas, and one in which you and I have worked at directly, which is dark energy. The biggest mystery, the biggest surprise in cosmology, and I would say in the last 50 years. It is an amazing surprise that the dominant energy in the universe appears to reside in empty space. But I say it's a surprise, and I don't think I ever asked you this. We wrote a paper, but I don't know whether I've asked you this time. The reason I thought that paper was important was it said, let's take all the data in cosmology, and it's not consistent with the universe unless there's dark energy. We had the one assumption the universe was flat, but we were convinced by inflation that it had to be. But I took that to mean, at the time, that some of the data was wrong. Did you think that at the time? I don't think I ever asked you. We wrote this paper, but I never asked you about it. And maybe in retrospect, it's hard to remember. But what was your take at the time?
Well, it was not that. It was not that some of the data had to be wrong. I felt it was Sherlock Holmes. When you've eliminated the impossible, whatever remains, however improbable, whatever the quote is. And I had already written, you may not remember this, it's one of my least remembered papers, although Wendy Friedman remembers it a lot. We looked for another solution. So we had this puzzle that inflation and a flat universe, it all worked, except there wasn't enough matter to make the universe flat. And so I wrote a series of papers. I'll just mention the other one because it links into what you said, which is the Hubble constant is 30. It turns out that works really, really well. Yeah. And that solution, if you ignored the direct measurements of the Hubble constant, that solution worked until Planck came along. You could always look at the data on the microwave background from an earlier experiment, WMAP, which is a fantastic experiment, and they always had trouble without prior knowledge of the Hubble constant ruling out that we had a very low Hubble constant. And so that was the other solution. That definitely fits into your category of a piece of data is wrong.
Yeah.
And it was a hard paper to get published.
Probably because at the time, no data pointed towards a Hubble constant of 30, probably.
I think it was really Joe and I, but there were a couple of other authors whose names came earlier. No, I'm not accusing them of not doing any work, but Joe and I were the senior authors. We had a little different view on it. Joe wanted to cast aspersions on the measurements and say, here's how it could be wrong. And I realized I didn't have the capability of doing that. And also I thought we'd really piss people off, because you're not going to get to 30 unless you invent some incredibly new thing that everyone overlooked, which we didn't. So we had a little bit of hard time. And I think at the end of the day, I'm going to have to ask Wendy this. I think she might have been the referee. And when we relaxed our criticism of experiments and just saying, let's suppose. But I think with Lambda, I became more and more convinced, because it solved so many things.
It looked right. I remember we talked about it. I think we had to, I don't remember, but I remember it took us about a year, but from the time we started talking about that, I think to convince ourselves, but everything we did made it look righter and righter and righter. Absolutely. And
it looked really right. And there was a meeting at Princeton. I got to represent Lambda against all the other solutions, and I won.
By the way, to do us further credit, I mean, this problem of reconciling with a flat universe was not, we had a lot more data in 1995, and we were able to compellingly use that data to argue. But you will remember more than a decade earlier, the first paper we worked on together when I was still at Harvard, one of the things we were trying to reconcile a flat universe. And at the end, we kind of threw it in as a, well, maybe there's a, cosmological constant, but it wasn't something, And Jim Peebles at the time, I think at the similar time, in fact, had argued the same thing.
Yeah, 1984. And it was belief. I think this is something important in science, and it's a very delicate thing in science, is that one of the predictions of inflation, the lumpiness is really a big one, but an equally big one is that the universe has the critical density.
Yeah.
And so at this Princeton meeting called Critical Dialogues, actually, it's too bad they didn't, people didn't stream meetings then, because the question was, does inflation predict a flat universe or not? And you will not be surprised that Andre Linde said no. Andre Linde also said at that meeting, but he said it many places, data cannot rule out inflation, only a better theory. And okay, it's just, Andre's a really good scientist, and I kind of understand what he's saying, and I don't completely disagree with it, but it's not the right thing you say in front of people who actually make real measurements.
Yeah.
Alan Guth was at Critical Dialogues, and he was asked, because he invented inflation. So what do you say, Alan? At the meeting, he said, inflation could have omega less than 1. It's not.
I remember, because people were,
He relented, but not in writing, and never again. And I remember telling, I probably shouldn't reveal this, but it's a theorist's secret, is that, Alan, now is the time to double down. The microwave background is about to reveal it. If you're wrong, you can now pull out of your back pocket a paper that says omega's less than 1. But if you're right, somebody's going to remember this is not a prediction of inflation. You said it could be flat or not flat. And so now's the time to double down. And in all seriousness, again, if you got a group of people who are experts, they would say you could have an inflationary model with omega less than 1, but that defeats the whole purpose. And if you're really looking for the big features of inflation, one of the very big features that is that it predicts a flat universe. And so the reason we wrote this paper is that there was a lot of indications that inflation was right. The lumpiness. Was looking right. And the one that I was most influenced by was not the age. That was the one you were really influenced by.
Yeah, you were interested, I think, in the baryon.
There was some confusion on the baryon front, but there was a very powerful argument using clusters as a fair sample. And by then we knew the baryon density very well. And so if we used clusters as a fair sample, we could figure out how much dark matter there was in the universe, and it was 30%. And it did depend on the Hubble constant, which is what led to the low Hubble constant universe. Yeah. So I think I probably believed in it more than you did, but I wasn't going to die if on it.
It just looked more. I guess I believed in it, but I was shocked that it was right. Having said that, that'll take us to close to the end of this, because dark matter's there, dark energy is clearly there. But I argued at the time, everyone said, we're going to know within a decade, if it's a cosmological constant or something else. And I said, no, this is going to be a much more complicated thing. We're not going to know in a decade. Everything's going to make it look like it's constant, and even if it isn't, and if it isn't, it's got to be so contrived to be able to be so far away from constant. Just now strikes me anyway. So I had this long. I still think it's going to be observed to be constant. But I think, as Dennis Overby told me, you were the one who convinced me to write the story. There's some measurements now that suggest that maybe the dark energy isn't constant. My attitude is that that's going to go away. What do you think?
Precision cosmology is really, really hard. And this DESI experiment, this is an experiment, it has a goofy name, Dark Energy Spectroscopic Instrument. So it's an incredible instrument for an old telescope that it was built, and it measures thousands of spectra at the same time. It really is a beauty to behold. The only handle we have on dark energy is measuring the expansion rate of the universe. And so it's measuring the expansion rate of the universe. And the one thing we know about dark energy is it's really important today. This is the first chink in the armor of lambda. So the idea that it is just a constant, that it's just lambda, for 25 years, every experiment has said more precisely. So the experiments have gotten more precise. Every experiment has said, yep, it's lambda, not 20% error bar, but 10%, 5%. The most recent one before this was 3%, but you get the idea. I'm not sure I believe the 3%.
Yeah.
Their best fit to their data, which is really good data, it's 1 year from this really important experiment. They've got 2 more years that they're analyzing as we speak. This 1 year of data, the best fit, and it's significant, statistically significant, is that dark energy varies. That would be monumental.
It would be monumental. That's why it's going to be wrong.
One quote that Dennis didn't put in the New York Times is, I said, oh, this is so fantastic, but I think my heart's going to be broken for learning something. I mean, we haven't learned. I mean, I don't want to say this in a negative way, but we've learned very little about dark energy.
Zero. I mean, that was my point, is that the only way you learn anything is if it's different than one. If it's different than constant, we won't talk about omega here, but if it's different than constant, is the only way you learn anything. Because if it's constant, it doesn't still tell you if it's fundamental or just something that looks like it's fundamental. But unfortunately, I thought, and I kind of still do, that unfortunately that uncertainty will remain. And I still think we're going to have to wait till we have a good theory.
Well, but we're going to know, because they have 3 more years of data. Sorry, two more. It's a 5-year survey. They have 2 more years that they're analyzing.
Yeah.
And this experiment, which was motivated by the discovery of dark energy, it was not the only big experiment that was motivated. So there was, I forget the official name now, the Rubin the legacy survey of space and time at the Rubin Observatory. That new telescope is going to have first light in 2026. There's the Euclid satellite, which the Europeans launched to study dark energy and dark matter. There's our satellite, the Roman satellite. We're going to know if they're right or wrong.
Yeah, we're going to know if they're right or wrong. And my attitude is somewhat the same as yours. As a theorist, I hope they're right in a sense, because it tells us something profound. But if I were a betting person, I would bet they're wrong. And I'm happy to have a bet with you about it.
I'm sowing one of my joys. I think I mentioned to you that I taught cosmology at UCLA this year. And I had a fantastic class of juniors and seniors. And so I'm working with one of the students. We're having fun. We're having a lot of fun looking at the data and trying to make sense of it. 2 things from a theory side is there's this silly way to look for changing dark energy that's really silly because it leads to crazy answers. And is there a better way? But we're also looking at the data, and the data look a little goofy, and the best fit model looks a little goofy, because the best fit model, and they'll tell you this, their best fit model to explain what they see is that dark energy was really unimportant in the past. Now,
Yeah.
you already know that. You already say lambda's unimportant. It's more unimportant.
Important, yeah. And that's goofy.
It's also going away in the future. So I could show you a graph here. So lambda looks like this. Their best fit model looks like that.
Oh, great. So it's anti-Copernican. It says we're at this, it happens to be just right for us now.
Well, no, it actually was at the birth of our solar system.
Well, that's not so bad.
It was a few billion years ago.
Yes.
And it's partly the reason that we're focusing on the model they use to analyze it is that the model they use to analyze it, if you look at very early and very late, it's going to tell you crazy things. So it's not a good parameterization. So I'm having a ball working with this undergraduate. She's extremely good, and he's taught me how to use Python.
Oh, great. Oh, well, that's the great thing about students. Eventually they teach you things. I miss that.
So we get up at the blackboard, and so we're just kind of playing around, trying to see. I'm a little bit worried that I'll get my heart broken because I look at the data, and I would be hard pressed if I showed you the data. I'm not going to show you the slide, but you would say, see, I told you so. These precision measurements are really, really hard.
We'll see where that is. I want to, in the interest of time, I'm going to leave dark energy in the last puzzle, which I want to do only in a minute or two. We began talking about the Hubble constant in some sense, in one way or another, in the context of BBN and other things. When I was young, the Hubble constant, as I said, was measured to be 100 plus or minus 5 or 50 plus or minus 5. And what I said and many other people, well, it's going to be 75 plus or minus. Well, it turned out to be close. Now, there are different groups who argue now not at the factor 2 level, but at the factor of 2% level. One group measures it to be, and we don't have to go into details, of 72, and another one 67, but the uncertainties are plus or minus sort of 2 on or maybe 1.5 on each side. And some people think that's significant. Again, being the old curmudgeon that I am, I say I remember back when there were factor 2 different. This 2%, it's going to resolve itself, but nevertheless, there are tons of newspaper articles and papers saying this is some fundamental tension in our current picture. Where do you stand on that?
So it involves measuring the Hubble constant with the microwave background. And what's wonderful about that is you're really measuring it way back when, and then using this well-established theory of lambda and cold dark matter to extrapolate it to the present. And you get a value of around 68 with a very small error bar, very small. And then you can directly measure it. So that gets a little complicated. So Adam Rees, Nobel Prize winner, discovered the universe is speeding up, gets a value like 73. And they differ by, it doesn't really matter because of what you said earlier, 5 sigma, but if they agree, it's going to be because of some systematic. Adam says to me all the time, Michael, this is just like 1998. I said, but one number made it all work. So adding lambda, and there's no good reason not to have lambda, but adding lambda solved 4 or 5 things. And here you add early dark energy. It doesn't matter what we call it. You could call it asparagus. You add asparagus, and it solves one thing, but it doesn't even really solve it. If you go back and look at our paper, oh my goodness, adding lambda, 30% chance that something's wrong with the microwave background measurement.
Mm-hmm.
That it's largely the Planck, and it's very complicated to analyze, and it's probably right. 50% that it's the Hubble constant today, and 20% that it's something new, like in 1995. But it's a real puzzle.
It is a puzzle.
And I would, in 1995, lambda really fit. You put in one number and you explained a lot of things, and you really explained it. What really, I give Adam really a hard time on this. If you look at all the papers, they add early dark energy, and it almost gets 68 up to 73. It doesn't quite do it. And now you say, oh, but there are error bars. So if you go back and look at our paper, you add lambda and everything comes together. There's no wishing and hoping. And I learned the lesson we were talking about back in 1995, Joel Premack, and his solution to cosmology was hot plus cold.
Yeah, that's what I was
But it
debating at the
didn't
time.
really work.
It didn't work. I know, but boy, they promoted it.
I think this is really exciting. There are cosmologists like, I mentioned Rocky Cobb earlier today, who mainly are physicists, who call the Hubble constant a nuisance parameter. And it's kind of an inside joke. It's kind of an inside baseball joke because often you don't really need to know the value of the Hubble constant to do what you're doing. And so it's kind of a ha-ha inside joke. But Alan Sandage, who was the protagonist for 50, who tormented many people, and people said of Alan, he was willing to move the Large Magellanic Cloud to make the data get 50. And he was strong enough to move the Large Magellanic Cloud, that I know. It is still the most important number in cosmology, and I think you would agree with that. Remember Feynman talking about if civilization ends and we could pass one fact, it's atoms. If we could pass one fact about cosmology, I think it would be the Hubble constant.
It tells everything about the universe, the age, everything. The universe looks the way it does because the Hubble constant is the value at, roughly the range it is. I agree with you completely there.
And it tells you the universe is expanding, had a beginning. It tells you how big it is, how old it is.
In fact, I disagree with Feynman. I think it's more significant than the fine structure constant. But
but Feynman is talking about atoms. His quote is about atoms. And so if you're talking about physics, if you're talking about cosmology, it is the most important number. And it's hard to measure. And I think you overstated the quality of the error bars in the days of 50 versus 100. It was a different game. And so I think you have to believe they're error bars, but you also have to say there could be it's the unk that's going to kill you.
It's the unk, exactly, the unknown unknowns. And they're the most interesting, and you never know. Well, look, having that allows us to sort of sum up. Do you think it's the best of times, the worst of times? We used to say it was the golden era of cosmology when you and I were younger. Is it still the golden era, you think?
Well, the golden age. And I stopped saying that. I was an early adopter of that, but then somebody told me, I mean, that's the trouble with scientists, is we don't take enough humanities courses, is that golden ages happen and then bad things happen. You don't want to call it a golden age because you're saying so I think it's very exciting. Well, let me give you an analogy in astronomy. Astronomy used to be really romantic. You would build an instrument, you would go up to the mountain, you would hope for good weather, you'd put your instrument on the telescope, you'd get clouded out, you would think, and now in astronomy, the data gets mailed to you either from JWST or Hubble, or even from an observatory, and cosmology changed. You let me, early on, I called it industrial scale science now, and it was really fun. You could work on a bunch of different things, and you could really be on top of a bunch of different areas. And now it is very, very specialized, and there are many people involved, but it's still exciting because we're learning about the universe. But it's exciting in a different way. And the big discoveries are going to come more slowly. You've seen that in particle physics.
Yeah, exactly. My big concern was that the standard model of cosmology would become like the standard model of particle physics. Everything would work, but we have no idea why. And maybe, and we in particle physics, we've been looking for 50 years for something to not work, to tell us what the right direction is. And I was worried that might be the case in cosmology, and I don't know. I hope it isn't, but one never knows.
It's still a very exciting adventure. And, I once had a slide that I used to show about cosmology, more so than other fields, is boom or bust. The universe is very often just beyond the reach of our most powerful ideas and our best instruments. And so if one or the other changes, you get a whole new glimpse of the universe. But it is really, it's amazing. I mean, if we lived on Venus, we wouldn't know we wouldn't know much about the universe. It's really cloudy there all the time.
Well, look, I'm lucky to have you as a colleague and friend, and this was everything I hoped it would be. It reminded me, well, I told you some of my favorite papers were written with you, how much I enjoy talking to you. And I've done a lot of discussions with scientists about, and I think this has just been one of the most fun, and I really appreciate it. It's been great. And I want to chat again and write some more papers.
I'm exhausted, but I really, really enjoyed it. And we do have that kind of little resonance. And I remember going back and forth because I do not, unlike Steve Weinberg, we were talking about Steve Weinberg, there's some famous quote from him or somewhere he says, most of his papers are single authored. And he explained why is he doesn't like the way other people write. He wants to say it his way.
Yeah.
And I get great joy because I start in one direction and it's often, almost always not the right direction, but it's the interaction with my colleagues. And I've enjoyed them with you. And the social aspects are not only just fun, but they contribute to the product.
They're absolutely. Science is a social activity. One of the biggest misconceptions people have is that it's single people working in the middle of the night. It isn't. And thank you. I think that's demonstrated. I hope that our discussion has. I hope it's as fascinating for others as it has been for me. It's, as I say, it's always a joy, and really, yeah, you rekindle my excitement if I on the days I lose it. So that's great. Thanks a lot, Mike.
Okay, great. And I've got to run now, but
Me too. I got to pick up a pizza in 1 minute, but thank you.
Oh, okay. Well, get that pizza. Otherwise, make sure they have all the toppings on it that you're supposed to get.
Thanks. As the Origins Project continues to reach millions of people around the world, I just want to say thank you. It's because of your support, whether you watch or listen, that we're able to help enrich the perspective of listeners by providing access to the people and ideas that are changing our understanding of ourselves and our world and driving the future of our society in the 21st century. If you enjoyed today's conversation, please consider leaving a review on Apple Podcasts or Spotify. You can also leave us private feedback on our website if you want to see any parts of the podcast improved or changed. Finally, if you'd like to access ad-free and bonus content, become a paid subscriber at originsproject.org. This podcast is produced by the Origins Project Foundation as a non-profit effort committed to enhancing public literacy and engagement with the world by connecting science and culture. You can learn more about our events, travels, and ways to get involved at originsproject.org. Thank you.